Look out your window, and the world is a wildly unpredictable mess of weather patterns, traffic jams, and noise. But if you walk behind closed laboratory doors right now, scientists from Tokyo to Toronto are operating from an exact, mathematically flawless playbook. This shared playbook is vital. If a metrologist measuring atoms, a chemist synthesizing a drug, and a clinician evaluating a patient do not use identical terminology, tiny discrepancies compound. A measurement misunderstood in early discovery becomes a cascading error that can derail an entire clinical trial. History is full of these structural breakdowns. Take the coefficient of Haze, an old metric used to measure airborne dust. Scientists eventually realized the data was completely skewed because aerosol particles interfered with the light transmission readings. The metric became a scientific dead end. Yet, if you look in modern scientific glossaries, you will still find definitions for the coefficient of Haze. They remain intact not as current standards, but as vital historical trail markers. They tell future researchers exactly what failed, preventing them from reinventing flawed methodologies. To pull predictable reality out of messy, chaotic theories, researchers rely on a unified scientific framework. It is an integrated dictionary that scales from the absolute microscopic physics of a single atom all the way up to the macroscopic behavior of human consciousness. Before we can understand complex biology, we have to establish the ground rules. The entire universe of scientific measurement is anchored by a metrological bedrock, fixed numerical values that act as the structural foundation for reality. For over a century, our measurement system relied on physical artifacts. The global definition of mass was a metallic cylinder sitting under nested glass domes. Because it was a physical object in a Parisian vault, it accumulated microscopic contamination over time, meaning the universe's baseline weight was slowly fluctuating. Our physical rulers were failing us. To fix this, scientists achieved an extraordinary global consensus in 2019. Gathered together, they agreed to scrap the metal artifacts entirely and redefine the foundational constants of science. To do this, they counted the atoms inside perfectly round silicon spheres. This allowed them to detach the Avogadro constant, the conversion rate between a substance's volume and its actual number of atoms, from physical objects. It was locked in as a pure mathematical truth, exactly 6.022-14076 times 10 to the 23rd per mole. Grounding the Avogadro constant in pure mathematics, rather than a piece of metal, removes the vulnerabilities of the physical world. It provides a universal, unchanging baseline that allows every subsequent chemical and biological experiment to start from the exact same starting line. Once the mathematics are locked down, the focus shifts to physical structures. But you cannot simply put a complex molecule under a standard microscope and snap a photo. These structures are too small to reflect visible light. By hitting a compound with an energy beam, researchers reveal its chemical identity. The colored light scatters into specific patterns within a spectrum's fingerprint region, from 1500 to 400 inverse centimeters. When these unique bands match a known profile, the substance identity is confirmed. With the 3D shape confirmed, scientists still need a way to draw it accurately on a flat piece of paper. To do this, they rely on rigid blueprints, like the Fisher-Rosenoff convention, an arbitrary but universally adopted set of rules that dictates exactly how three-dimensional atomic bonds should be represented in 2 dimensions.
These highly specific spectroscopic tools and strict spatial drawing rules serve a vital purpose. They guarantee that a manufacturer in one country can synthesize the exact same complex compound designed by a lab in another without introducing structural errors that could render a drug toxic. Transitioning a verified molecule out of a sterile laboratory and into a living host introduces an entirely new level of complexity. The moment you swallow a pill, it immediately crashes into the body's first line of defense, a highly acidic, hostile barrier starting with your stomach. If a chemical survives the stomach, it runs straight into the first pass effect. The liver acts as an aggressive biological reverse assembly line that actively dismantles unfamiliar foreign chemicals before they can enter your systemic blood circulation. Inside the cellular factory, the liver recruits molecular helpers, known as cofactors. These organic tools facilitate the enzymes working on the assembly line, stripping the invading chemicals down into water-soluble pieces for the body to safely excrete. Understanding this gauntlet explains why a true first-in-class drug, A medication hitting a completely novel target in the body is an engineering marvel. The molecule must be perfectly engineered to survive the acid, slip past the liver's biotransformation, and successfully bind to a specific cellular target located deep within the body's coelom, the central biological cavity where vital processing occurs. To achieve pharmacological success, a compound cannot just work perfectly in a beaker. It requires an incredibly precise chemical blueprint, capable of anticipating and outmaneuvering the inherently aggressive physiological barriers of the host. This chaotic biological defense system stands in sharp contrast to the reliable physics of physical matter. In thermodynamics, behavior is uniform. Equations like the Avrami equation can flawlessly map out the kinetic variables of crystallization, telling you exactly when and how a material will change state. This is a chart illustrating a first-order phase transition. You can see the energy of two phases matching perfectly at a specific temperature, followed by an instantaneous snap in the rate of change. It is a violent, mathematically certain break, like water hitting the boiling point and instantly flashing into steam. But as we scale up from basic molecules to the functioning human brain, that mathematical certainty disappears. The study of human cognition relies on deceptively simple physical proxies. To measure complex neurological processing, scientists use raw physical outputs, like the rate of a finger-tapping test, or observe associative learning through behavioral avoidance tests. This is the ultimate boundary of our mathematical models. You cannot plug human memory or anxiety into a clean flaneur and get a predictable result. Consciousness adapts. It forgets, and it frequently behaves completely irrationally, heavily resisting the clean parameters of physical thermodynamics. The universe is a messy place, and biology is its most complex expression. A unified scientific framework is humanity's essential tool for imposing a shared language onto the unknown. By rooting our reality in perfect mathematical constants and strict chemical rules, we construct a reliable bridge through the chaos, giving ourselves the necessary footing to explore and treat the unquantifiable human mind.